Perfect. Okay, good. Well, we'll get most of it. Okay, so I missed the first part of this, but there it is. And so now I'm going to give you the notation for infinitely many objects. Or not. These things are always so hard to work with. Okay, let's try that again. Sorry, guys. I think that's going to be a little more stable now. Okay, you could have infinitely many of a particular object, so I just want to give you that notation as well. So an unlimited number of whatever x is, whatever that's denoting, is written, not surprisingly, we'll just write that as infinity times x. So you're just putting the number of repeats in there in front of it, an infinite number. Okay, so let's do an example that involves multisets and permutations in a multiset. And we've seen some examples like this already. I'm just going to now doing it formally in the context of this section. How many 7-letter license plates are there? Okay, so this is a question. Not a hard one, but just to kind of get going here on this. So if we wanted to solve this, what do you suppose we might want to do? I don't want to know the answer yet, but like, what would be the setup of it? How would you picture it? Yeah, I'd write down 7 slots and then figure out how many choices there are in each slot, right? So you could draw 7 slots. Okay, so I'll actually do that. 1, 2, 3, 4, 5, 6, 7. And then I have to fill in the choices here and of how many ways there are to fill in each slot. So how many letters are there in the alphabet? 26. So, and there's nothing that says you can't have the same letter more than once. So this is repetition allowed, but on a license plate, the order of the letters would make a difference. So that is the characterization we're in here. So we would have 26 choices, which of course would be from A through Z. Okay, and that would apply to all of these slots. Okay, and so we would go all the way across. And so what would my answer be?
26 to the 7th.
Exactly, 26 to the 7th. Whatever that is, I don't even care. I just want to have it written this way. 26 to the 7th license plates. Okay. Can I rephrase the question using some of the notation that I gave you? I think I probably could. Let me just see if I can do it here, just so you can kind of see how that would look. Rephrase of this question. We've already got the answer. I'm rephrasing the question after already having the answer. But the idea would be, we're asking really how many 7 permutations. So these would be permutations that have 7 slots, right? Are there of, and then what we would do is we could write it as a multiset, and we can have as many A's as we want, as many B's. There's an unlimited number. I mean, technically, you're not going to need more than 7 of any letter, but in the strict sense of the word, we have infinitely many A's, infinitely many B's, infinitely many C's, and so on up to infinitely many Z's. And this becomes the set that you have. So you're asking for the 7 permutations of that set. Unlimited numbers of every letter of the alphabet. You can pick the same one again and again and again. And we're talking about permutations because order matters. And there's 7 slots. That's it. So it's pretty easy. So let's just state as a theorem then, sort of the general principle that we have here. So this is theorem 2.4.1 for those of you who are playing along with the book at home. And this is just going to give us the idea that this example illustrates. Namely, let S be a multi-set with objects of K different types. So you have K different types of objects. So like in this example over here, K would have been 4. There's some A's, there's some B's, there's some C's, and there's some D's. It's just a number of different types of objects that you have. And then I'm just gonna say each with infinite repetition. So in this multi-set, you have every one of these types of objects as many times as you want. So there's infinite repetition. Then the number of R permutations of S is, well, for each of my R slots, I have K choices, and I never run out of any objects, so I can keep having K choices again and again and again. So the answer is K to the R. That's the formula. And so we have our example there on the left that kind of just illustrates, pretty much just illustrates this principle. Let's just do one more practice example just to make sure we're all good on that. We don't always have to so formally, set up the multi-set. You can just draw your slots and say, well, how many choices do I have? But you're really doing this principle here. Yeah. So let's do another example just to get everybody warmed up today for this. So, yes.
As a homework solution, would you like us to draw the slots, or can we just say, imagine, you have 7 positions?
I don't have to see those slots. I like to just for myself visually, but if you want to, as long as you're writing an explanation, I'm okay without those slots. Yeah, I still think for most people, it's helpful to draw them. Yeah. Okay, let's do another example. So a witness to a hit and run. Here we go. Accident. A witness to a hit and run accident reports the license plate. The license plate has 3 digits followed by 3 letters. That's the first thing. There's a little bit more to it. So 3 digits followed by 3 letters. It does contain a 4 and a 9 in it somewhere. So the license plate has a 4 in it, has a 9 in it, and no vowels. I don't know how realistic this is. You see a hit and run accident, are you gonna be looking to see if there's any vowels in the license plate? Probably not. Anyway, but just for the sake of making my question work, I just had to do that. So there it is. And the question is just how many plates are possible? How many plates are possible? So this is going to combine a few different principles that we've looked at up until now. I just want to kind of put them together. What do you think the first thing is we should do? Draw a little visual of it. Yeah, I'll draw some slots, right? How many slots do I need? 6 slots, because I've got 3 digits followed by 3 letters, right? So draw 6 slots. So I'll just go ahead and do that here. I'll make them nice and big. And what we know is that the first 3 slots are digits. I'll go ahead and remind myself here that that's the case. And then at the bottom, we're going to have the letters in the last 3 slots. Okay, so we can kind of just label it like that. And let's see. Do you want to talk about the digits first or the letters first? They don't really interact, so you can count either part of them independently, and then of course we'll use the multiplication principle. Want to start with the letters? Okay, let's start with the letters first, doesn't matter. Do whatever we want, let's start with the letters. Try to keep my colors here. So for the letters. What are they telling us here? They're just telling us, all we know is that there's no vowels. So if there's no vowels and I'm filling in these 3 letters, how many choices would I have for that portion of completing the license plate? 21, right? Because there's 5 vowels and out of the 26 letters. So that's, take those out. We have 21 non-vowels. And because we can repeat, there's 21 choices here, 21 choices here, 21 choices here. So basically K is 21. There are 21 different types of objects, which are just all of the consonants. They all have infinite repetition. We can have as many of them as we want. And we're talking about 3 permutations, right? So that's going to give me 21 cubed by theorem 2.4.1, just to make a reference to that. And that will need to get multiplied with the choices for the digits. Now, what they told us is that the digits, so let's look at the digits now. The digits have to contain a 4 and a 9. Okay, so I have to think about how to cleanly count the number of things that could happen here. Does anybody want to propose how to kind of organize that part of it? Got an idea?
So the 4 and 9, there's 2 possibilities for them, but for the other 8 digits, only 1 possibility for them. So it'd be like 4 to the second, 9 to the second, 8 to the first, or yeah, 8 to the first. There's 1 possibility, 1 slot for the 8 numbers, 2 slots for those numbers. Because repetition's allowed, right?
Yeah, so we could have 2 4s and a 9, we could have 2 9s and a 4, or we could have 1 4, 1 9, and some other digit.
Yeah,
When you hear me using the word or,
it's adding.
adding, right? Yeah.
I mean, yeah, I guess I was gonna say, you choose a spot for the 4, then a spot for the 9. And then
Okay.
by 9 digits, right?
Yeah, so, well, I have to be careful because if of those other 9 digits, if we choose the 4 again or the 9 again, that's kind of a weird case. What I would do, guys, I always rather solve several easier counting problems than trying to, in one breath, get the final answer out of a complicated situation. What I would recommend that we do is we figure out how many ways there are to do the digits where none of them are the same. We have a 4, we have a 9, and we have something else. I would figure that out, and then I would go back and say, well, what if we have the 4 and the 9, and then another 4 or another 9? Because there aren't going to be very many of those. I could probably just write them all out, actually. So let's do that, right? Let's do that. So cases. So case 1. So when you do cases, you're basically saying, I'm going to solve a bunch of smaller problems and add the results, right? Case 1 would be all digits are distinct. And so I like what Marcus is saying here was that we can pick where the 4 goes, pick where the 9 goes, and then we'll have 1 slot left and pick a different digit. So what we'd have here is 3 choices for placing the 4. It doesn't really matter which one you start with. Let's just say we start right. So I'm going to either put the 4 here, here, or here. 3 choices, right? And then we would have 2 choices left for placing the 9. And now we have no choice left about where the 3rd digit goes, but now what we have to choose is which digit is it? And if all digits are distinct, then we can't have another 4 or another 9. That means there's how many other digits? 8, right?
Yeah, 8.
So then 8 choices, not for a position, but for the 3rd digit. And that 3rd digit will have to go into whatever space you left for it, because you've already put the 4 in, you've already put the 9 in. And so you only have one spot where there could be a different digit. So that's one choice, but then beyond that, you have to choose which digit it is. Okay, so then I'm gonna take those choices, guys, and in this case one, by the multiplication principle, I'm running out of room, I'm just gonna write MP, right? There are. What is it? 3 times 2 times 8, which would be 48. Plates, sorry, not really full plates, just the digits, okay, so 48 choices for the digits, that's what I'm trying to say. That's in case one. Yeah? I like that because it's just easier. I don't have to worry about whether the 4 or the 9 was repeated and all that kind of stuff. They just assume it's not the case. Case 2 would be some digit repeats. So either there's no repeats or there is repeats, right? It's either yes or no. Make sure that when you do cases, make sure you have covered every scenario by your cases. Here you clearly have, right? Because either all the digits are distinct or there is at least some digit repeating. In this case, if I have a digit repeating, then that would mean that my 3 digits are only consisting of 4s and 9s, and you have at least one of each. So honestly, it's easiest to just write them out. Okay, so I mean, sure, you could come up with a little counting problem for that, but I think it's just easiest to write them out. I'll write them in increasing numerical order. So I could have a 4, and a 9, or I could have a 4, a 9, and a 4, or I could have a 9, a 4, and a 4. Those are the ones that have 2 4s and 1 9. Or I could have 4 and 9 and 9, or 9 and 4 and 9, or 9 and 9 and 4. And so there are 6 choices for digits here. Make a little bit of sense? It's just easiest to just write them all out in that case. So you've got 48 ways in case 1, you've got 6 in case 2. So how many ways are there to do all of the digits?
48 plus 6.
48 plus 6. I'm adding the cases together, right? So there are, so by the addition principle, okay, there are 54 digit possibilities. "54 ways to do the digits. There were 21 cubed ways to do the letters. So now finally, what am I gonna do to wrap it up? Multiply, right? I have to use the multiplication principle now. The choices for the letters times the choices for the digits, because they're independent tasks, subtasks of the whole thing. And so I guess I'm gonna, you guys don't mind, I'm just gonna come up here, wrap this up. So what we would have here at the end of this is that's very strange. What we would have at the end of this is, by the multiplication principle, there are 21 cubed times 54 plates. That's a lot. It's quite a large number. Okay, does that make a little bit of sense? The only thing we don't see in the answer anywhere is a combination. I could do that. What I could do is I could change the question and I could just say that a witness to a hit and run accident reports the license plate has 3 digits and 3 letters. Not followed by, but just 3 digits and 3 letters. And the same condition on the digits, the same condition on the letters. How would that change the answer? If I'm not saying it must be digit, 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 letter, letter, letter. That'd be a good follow-up question. Imagine we don't know which positions have the digits and which positions have the letters, right? So as a follow-up here,
Just multiply by 6 factorial.
we're gonna multiply by something, it's not 6 factorial. It's not gonna be 6 factorial. So, what if we don't know which slots have digits and which have letters? So just take. It's what?
That was, oh,
It's not doing what?
I just said it wasn't funny to me. You was.
Oh,
You
I
got it,
see.
Yeah.
Yeah, I see what you mean. Yeah, it's actually. I hope everybody's here today. I don't think this is gonna be a very good video. Kind of messed it up by dropping it. So. Any thoughts to how that changes my answer?
56, choose 3.
That's it. Yeah, that's it. I have to choose. If I don't know which slots have the digits, then I have to choose those slots. 6 slots available, choose 3 of them to fill with letters. And then of course, the other ones would have to be filled with digits. So the answer would be just the same answer as before. So the answer would literally just be. The answer here would literally just be 21 cubed times 54. That's all just like from above. And then we would just tack on 6, choose 3. And what we're doing here is choose 3 slots to have digits. Now, does everybody understand that once I choose the 3 slots that have digits, I don't really have to choose slots for the letters? Don't do another 6, choose 3, right? The single factor of 6, choose 3 chooses where the digits go, and then by default, the letters must take the other slots. Right? There's no more choosing at that point to make. So this would be the end of it. That would be the whole answer. Yeah, so that's pretty good. Okay. Is everybody okay so far? I'm gonna throw a wrench in it. Like I always do. What if the order sort of matters and sort of doesn't matter? Right? You can kind of have these fuzzy interface type questions. I'm gonna show you an example. Or what if, you could say the same thing about repetition. It's somewhat allowed, but not completely allowed. So let's do another example to kind of illustrate my point here. I think I'll just jump into the example. How many ways are there to arrange the letters of the word Mississippi? Has anybody been to Mississippi? Yeah. I have been to Mississippi. I have actually been to all 50 states. Actually, I have been to the highest point of 49 out of the 50 states. I'm still working on Denali. That might take a few years. But anyway, yes. So anyway, Mississippi, I've been there. And what if we wanted to figure out how many ways there are to rearrange the letters of this word? So you can see that repetition is sort of allowed. I have repeats of some of the letters, but the M, for example, is not repeated. And the order sort of matters. If I switch an M and an I, that'll give me a different word. But if I switch 2 S's, nothing changes. I don't want to count that twice. So I got to be a little careful about this. So let's talk about how we would do something like this. This is the standard combinatorics problem. You see this all the time. I really have 2 ways to explain this solution that are quite different. And so listen to both of them and see if one of them resonates with you more than the other. The first solution, let's just call this solution number 1, is to sort of pretend that all of the letters are different at first, that this is an 11, I think there's 11 letters here, that these are 11 different letters. And you could do that by kind of just putting subscripts on the ones that are the same letter. So you have an I1, 2, 3, and 4, you have an S1, 2, 3, and 4, and you have a P1 and a P2, right? You could just kind of pretend for a minute that they're all distinct. Okay, so solution number one is if we had 11 distinct letters. So we're taking away the repetition completely. We're no longer looking at a multi-set, we're just looking at a set. We have 11 factorial, right? That would be the number. 11 factorial arrangements. So if it was a word that had no repeats of any letters, then that would be the answer. And it's of course too big of an answer because we know that, for example, if we switch the two P's, it really shouldn't be counted twice. In fact, would it be fair to say that exactly half of these 11 factorial arrangements would have the P1 in front of the P2, and the other half would have the P2 in front of the P1? Right, just like the bride and groom in the photograph last week, right? Half of them have the bride to the left of the groom and half have the bride to the right of the groom. Well, that just means that right there you have doubled the correct number of answers. So this is already too big by a factor of 2. So what I'm going to do is cut it in half. I'm going to divide by 2 factorial. So to account, now I'm going to fix it, right? This is the wrong answer, but I'm going to fix it. To account for repeated P's, what I'm going to do is I'm going to divide by 2. It's too many P's, and as soon as I take the 2 distinguishable P's and make them look the same, I have to cut the total number of solutions in half. I'm actually going to write that not as 2, but as 2 factorial, if you don't mind. You'll see why in a minute. It's the same number. Because what if there were more than 2 of them? So let's talk about the i's, right? So to account for the repeated i's, now guys, I have 4 of those. And I could scramble those subscripts in any order that I want, and all of them should only count as 1 arrangement. You understand what I'm saying? So like, literally this word, the way I've written it, is one of the 11 factorial arrangements. But if I switch these subscripts and I do the 4 there and the 1 there and the 2 here and the 3 here, that's the same word. And so you can imagine scrambling the subscripts on those i's into how many different ways? 4 factorial, right? 4 times 3 times 2 times 1 in ordering the 4, 3, 2, and 1 on those subscripts. So we must divide here by 4 factorial. Okay, and then similarly, I'll just make a very quick note that for the s's, we would be doing exactly the same thing. We would be dividing by 4 factorial. So my final answer then, my answer to this problem that would be correct would be 11 factorial divided by 2 factorial, also dividing by 4 factorial twice. That would be an answer. So 11 factorial is assuming all the letters are distinct, and then these divisions are undoing that and acknowledging that you actually are overcounting because of the repeats. That's how that works. You guys can take any word and do that. It's pretty simple. You guys like that solution? It's pretty nice, but I'm going to give you another one now. I'm going to see if you like it better. Instead of sort of assuming I have 11 distinct letters, I'm going to lay out 11 slots and just start throwing the S's in, the I's, the P's, and the M's, and just see how many choices I have as I go along. Okay, so solution number 2, it's a completely different solution, is to imagine using 11 slots. We apply the multiplication principle, so I'm gonna do a little multiplication here. And the way this is going to work is, well, I can draw 11 slots here. 6, 7, 8, 9, 10, 11. I am gonna start throwing the letters in to the slots. So for example, let's say I want to do the subtask of putting the M into the word here, right? So there are, well, as you can see, 11 choices for where to put M. So you just put it somewhere, and maybe you put it there, doesn't matter. Now, okay, well, you, actually, it doesn't matter which order you pick these letters in, now I do the I's, let's say. I've got 4 of those, and I'm gonna do all 4 of them as a batch. So I'm gonna take the 10 remaining slots and choose 4 of them, not in order, just choosing them, and I'm gonna assume they all get filled with I's, right? So then there are 10 choose 4 choices for where to put I. Yeah. By the way, this 11 is really just 11 choose 1. Okay, so it's the same thing. Once I've done that, I should have, how many slots left? 6? Okay, and now I gotta put in the S's. So there are, out of those 6 slots, 4 of them I'm going to choose to put the S's. And then finally, there's only 2 slots left, so the last one you won't have any choice about. You have to do the 2 choose 2 for the P's. So you must put the P's in the remaining slots. And so here the answer by the multiplication principle is that we get 11 times 10 choose 4 times 6 choose 4 times 2 choose 2 arrangements. I might point out that I didn't have to start with the M and then the I and then the S and then the P. So you could probably come up with some alternative answers. An alternative answer, for example, maybe you start by taking the 11 slots and choosing the 4 slots for the I's right away. And then maybe you decide to go to the, so I'll just put I there. And then maybe you decide to go to the P's next. So you have 7 slots here, you choose 2 of them for the P's. Now you got 5 slots left, maybe you choose 4 of those for the S's, and then you got just 1 choose 1 for the M's. And so that should also be the same answer. So just conceptually, I mean, even without getting out a calculator, it should be reasonable that these would actually end up being the same number. And if you wrote out, if you did the, you know, the usual formula for the combination, and you spell out all these terms using the factorials like this and started canceling away, you'd get all the same things that survive the simplification. You see a little bit here why combinatorics can be a bit of a slippery subject. We're talking about permutations, and yet our answer, in this version at least, has combinations in it. So that's a little bit maybe counterintuitive. Like I would be expecting, like in that sense, maybe the first solution is a little bit more aligned to what your intuition would tell you, which is that when you do permutations, you're thinking of factorials rather than combinations. But you know, again, it's nice to see different perspectives, right, on the same problem. Let me ask you a slight little follow-up again. I just love we get to do so many practice problems, and these are just so much fun. Actually, before I get to the follow-up, I'm sorry, I forgot one little remark here that I meant to make before I go on to the second problem. My fault. If we have like the total number of slots, which is you know, n1 plus n2 plus dot 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 dot. So in this case, it would be I don't mean to make a big parentheses, there's just a little parentheses. In this case, we would have, you know, 1 slot for M's, 4 slots for I's, 4 for P's, and 4 for S's and 2 for P's. If you add all those up, that's 11 slots And now I'm gonna put the factorial on the 11, right? And then if I divide by the number of these, by each of these numbers factorial, so this is a n1 factorial times n2 factorial, n3 factorial, and dot, 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 up to n sub k factorial. That's really giving you the first solution. Right, so the n's are representing how many repeats of each type you have. So we have n1 is the number of m's, n2 is the number of i's, and so on. So this is kind of lined up with the first solution, but it's the same thing as if you had taken all of the slots. There would be 11 of them, so you add all of those up. For this example, it would be 11, and you choose n1 of them to put the first object, right? And then you come back and the second term, you've already filled in the n1 slots of whatever the first object was. So you're now left with how many slots are left? Well, starting from n2, adding up to n sub k, right? And now I'm gonna choose n sub 2. Yeah. I'm basically trying to line this up with solution number 2. And you go dot, dot, dot. And the very last one, you're down to n sub k, choose n sub k. So the very last one would just be like what we had here, 2 choose 2, or 1 choose 1, depending on which order your n's are in. Okay, so this is actually something that could be verified using the factorial formula for combinations. But it's just kind of common sense. Because these two solutions have to both be the same answer. They must be. Does everybody follow that? Seem reasonable? Okay, great. Now let me give you a quick little follow-up. I always like to do this kind of thing, and you'll see I do this on my exams too. You know, there'll be a sort of part A is kind of no constraints, just solve something basic, and then I'll give you a second part where you have to tweak it a little bit, just to kind of practice variations. So let's just do that here. I'm going to do a quick follow-up, which is going to simply be how many 10 permutations? How many 10 permutations of Mississippi are there? So remember, Mississippi actually has 11 letters. And so I'm saying, well, what if we only had a string of length 10? Any thoughts about, maybe I want to hear from somebody new, or somebody I haven't heard from yet. Any thoughts about how you might tackle this? I don't need the final answer, but just kind of like what would be a reasonable approach?
One letter to exclude and then find out how many ways you can do that letter and keep repeating it.
I love it. We can think about which letter is left out, right? Out of this word, we're leaving out one of the letters, excluding it, and then we can just count from there in each of the possible. There'd be 4 cases, right? Because you could leave out the M or the I or the S or the P. Yeah, I love it. I love it. Really good thinking. So solution, choose which letter to omit. And that's going to give me 4 cases. All right, I like it. Okay, so let's say we omit the M. That would be 1 case. So, you know, basically it's just a Mississippi problem without the M, right? So you've got, you can use either solution number 1 method or the solution number 2 method. So using, I guess I'll do solution number 1 method. So if I leave out the M, guys, I'm going to have 10 factorial if I treat them as 10 separate letters. And I divide by the repeats of the 2 P's, which is 2 factorial, the 4 I's, which is 4 factorial, and the 4 S's, which is also 4 factorial. So that would be the number of 10 permutations that omit M. Okay, but then instead of the M, we could choose to omit the I. right? Well, again, it's, 10 factorial, different letters. If I omit, and I'm only omitting one of the i's, right? So I still have one m, I'm gonna go ahead and put the 1 factorial into the m now. And I would have 3 i's left. I still have 4 s's, and I still have 2 p's. So 3 factorial, 4 factorial, and 2 factorial on the bottom. So that's just very similar. And then I just have to do this 2 more times. I'll go kind of quickly here if you don't mind, guys. So omit the s. Well, we can just say that's similar to the I. Because there's 4 i's and there's 4 s's. I'm just gonna say same as the I case. Save myself a little bit of effort. Same as the I case. And finally, we could omit a p from our string. Yeah. And again, 10 factorial goes on top. On the bottom, I have 1 m, I have 4 i's, and I have 4 s's, and I've omitted one of the p's, but I still have 1 p left, so that would be a 1 factorial. Notice how the numbers on the bottoms of the factorials adds up to the total number that you're factorialing on top. Right? I mean, that's kind of what you see here. If you take all these factorials on the bottom and add them up, you get what was on top. So that's what you're seeing here as well. What am I gonna do with the answers for these 4 cases? Add them up, right? So now use the addition principle. All right, I think I'm just gonna, I'll leave the rest of that to you as a little exercise. I mean, it's not really an exercise at this point, it's just writing it down. But anyway, that's all that's left to do there. Make sense? Okie dokie. Perfect. Questions? Well, now let's try the real, I guess a more challenging one that I think I used in my intro video that you watched before we kind of got together at the beginning of the semester. Let's talk about putting 30 people into 10 groups of 3. So here's another example, same kind of problem. How many ways to put 30 people into 10 groups of 3? I'm actually going to give you 2 solutions again. And they're going to line up with the same 2 solutions we had over here. So I'm going to do a solution number 1. The solution number 1 is going to have a lot of factorials in it. And then solution number 2 is going to have a lot of combinations in it. Okay. So if I had 30 people, let's just imagine that there's 30 of you here. One way that I could approach putting you guys into 10 groups of 3 would be, I can line you up in a line, 30 people, right? Straight line, 30 slots really. So I could make 30 slots. I don't think I'm gonna draw 30 slots, but I'll start. Right? So, I got Kevin, Jose, myself, whoever, anybody, right? Sam, Vivian, blah, blah, blah. By the way, if you haven't stopped by my office to introduce yourself yet, I'd love for you to do that in Zoom or in person. That way I could start learning all of your names. I know most of you. But let's just imagine we set you up in a line. How many ways would there be for you to stand in a line? It's basically a photograph question. If I have 30 people and I want to put you from left to right into a photo, how many ways would there be to do that? Yes? 30 factorial. What was your name again? Is it Mason? Mason, that's right. 30 factorial, right? So there would be 30 factorial ways to put 30 people in a line. And this is going to kind of represent the numerator of kind of how we did the Mississippi problem where we had 11 factorial. We imagined that there were 11 distinct letters, and we just put them in order. So I've got 30 people and I'm putting the 30 people in order, right? And then what I would do at that point is I would literally just chop and say, all right, after 3 people, you are a group. And then the next 3, you're a group. And the next 3, you're a group. And so on. I'd end up with 10 groups that way. So I would just by default, I'm not making any more choices. This is where my choices are. And I'm now just chopping the line every third person. And I'm saying, here's group number 1, here's group number 2, here's group number 3, and so on and so forth, right? But remember that when you're in a group, there is no first, second, and third person. So like in this first group, if this was, Marcus and Tanner and me, right here, Marcus, Tanner, and me, it would be the same group if I had been first and then Tanner and then Marcus. Right? So I have to account for the fact that if I scramble 3 people that are in the same partition here that I've created, then I really don't have a different group. And so I need to divide by 3 factorial, but I have to do that in each of the 10 sections that I created. So for each of 10 sections. And so that's actually 3 factorial to the 10th that I'm going to be dividing by. You see that? But, okay, so if this is Tanner and Marcus and Dr. Annan right here, right? And so we could scramble these 3 people, and that's dividing by 3 factorial. And I do that for every group of 3 that I have, right? I have another issue, which is what if actually Tanner, Marcus, and Dr. Annan were over here? That we had kind of gotten put together in this little section of the 3. Well, again, there isn't a first group, a second group, and a third group. Like there's nothing special about being here versus being here versus being here. We don't want to put these groups in order. Now, it could be that I might ask the question, how many ways are there to put 30 people into 10 groups of 3 and schedule them to give presentations during 10 weeks of a semester? And then you might say, well, if Dr. Annan's group has to go in week 1, that would be different than Dr. Annan's group presenting in week 3, right? So in that case, we actually would not want to take out the ordering, because we would actually say, well, this is different from this. But if I'm just talking about 10 groups of 3, then it shouldn't matter which group is kind of clustered first, second, third, and so on. So what else do you think we need to divide by? Say one more time. 10 factorial, right? You have sort of 10 objects, which are the 10 groups, and you need to unorder those, right? So I'm going to now divide by 10 factorial for the 10 different groups themselves. Okay, and so we get to an answer here. Again, I'm going to give you a second solution. So see how you like this one. If you don't like this one, I'm going to give you another one. But the answer should be 30 factorial all divided by 3 factorial raised to the 10th power times 10 factorial. And you could come up with a number for that if you really wanted to, but I will just leave it like that. Okay. But let me give you a second solution that is more lined up with the second solution to the Mississippi problem as well. I think this will be nice to see. So for a second solution, unless is there any question about that first thing? You're basically laying out 30 people in a line like they're taking a picture, and then you just have to divide out by what doesn't matter. The order of the 3 people within each group doesn't matter, and the order of the groups themselves doesn't matter either. So you take all of that out using division. Okay. But I have another solution, which is, so you guys help me with this. I got 30 of you, and I want to make 10 groups of 3. So I'm going to take 30 and choose 3 of you to be a group. Then I got 27 of you left. And so I'm gonna take 3 of you, and I'm gonna choose 3 of you to be a group. And then I got 24 of you left, I choose 3 of you to be a group, I go all the way down. Eventually I have 6 of you left, I choose 3 of you to be a group. And then the last group of 3 would by default be whoever hasn't been picked so far. Okay, so this would be choose a group. And then this one would be choose another group. Nobody gets to be in more than one group, so your numbers keep dropping by 3 each time. And then this is just et cetera. Okay. And so is that gonna be the right answer?
No,
What's the matter with it?
because you ordered the groups in a sense here.
Same problem we had over there. Somehow, in the first 30, I chose 3, so I chose Marcus, Tanner, and myself right here. Well, that makes us a group, but we could have just as well maybe been the last 3 chosen at the very end, the 3 that hadn't been picked so far. And that would not necessarily mean we had a different group, a different collection of 10 groups of 3. It's just they were chosen in a different order. Yeah, so the dividing by 10 factorial part still has to happen here as well. So I'm going to divide all of this by 10 factorial for the same reason that we did in the first solution, namely, to account for the 10 groups themselves. If you want a real simple example of this, because these numbers are kind of big, just ask yourself, how many ways are there to take 4 people and put them into 2 pairs? You're gonna play bridge for a group, I think it's a team game, 2 players each. So you have 4 players and you wanna pick teams, so you might think the answer should just be 4 choose 2. You got 4 people, choose 2 of them to be a team. And then, of course, the others would be automatically a team, but actually, this is 6, and that is not the right answer. If you have 4 people and you're trying to figure out how to make 2 teams out of 2, so you got A, B, C, and D. So you can have A and B as a team and C and D as a team, or you can have A and C as a team with B and D as a team, or you can have A and D as a team with B and C as a team. That's it. 3 ways to make teams out of these 4 players. We needed to divide this by 2 factorial, which is like the 10 factorial here. Okay, so that gets you to the right answer, which is 3, not 6. So if you want to do an example with small numbers, that would be it. Make some sense? Okay. All right, so I think that's what I wanted to say about multi-sets. These Mississippi type problems are pretty common, so be sure to practice those up for sure before the quiz. I think you're gonna see it on the homework anyway, so that'll be good. I'm going to, unless there's any questions, I'm gonna talk about combinations of multi-sets for a few minutes. Combinations is simply going to be order doesn't matter and repetition is allowed. Yeah, so I think that's the one thing we haven't talked about really. So this is 2.5 right here, so kind of go to the next section, which is combinations of multi-sets. And guys, on Thursday, we'll do some group work and practice some of these things together, but I'd like to get some of this material covered. So in this case, what we're talking about is order doesn't matter. Combinations means order doesn't matter. But if it's a multi-set, then repetition is allowed. Order doesn't matter, but repetition is allowed. So let's go back just to review really quickly. If order doesn't matter and repetition is not allowed, so that would have been combinations of sets. Right? So a set is one where you don't allow repeats. That would have been the poker cards, playing with a deck of cards. So we've got, it's kind of nice to think of your typical example, right? So if you're talking about combinations of sets, that's poker cards. If you're talking about permutations of sets, that's photographs. If you're talking about permutations of multi-sets, that is license plates. And now, if you talk about combinations of multi-sets, we're going to the grocery store to buy fruit. The example that I love to use. We're going to buy fruit at the supermarket, right? Buying fruit. Except I have to tell you, I usually do my shopping at midnight, and it is very often the case that repetition is not allowed. There's only one apple left. I have to pick that apple. I don't have a lot of choices. But anyway, let's just forget those details. If you go into the store to buy fruit, it doesn't really matter. All that you care about is what's in your grocery bag that you're taking home. I don't care if you picked up the apples first and then the pears and then the bananas, or whether you started with bananas first and then went to pears or whatever. The order does not matter, right? And at the same time, repetition normally is allowed. You can repeat, take several apples or several bananas. And so there is repetition allowed, but the order doesn't matter. Let's write that down. So assume an unlimited number of identical. Okay, that word identical is important because it's suggesting that we are repeating the object. So identical, let's say apples, oranges, and bananas. Okay, the question is, so here's my example then. The example is how many ways, oh, yeah, so I guess I'm already calling this an example. How many ways can we bring home 18 pieces of fruit? Okay. 18 pieces of fruit. I want to bring home 18 pieces of fruit. So I could pick 18 apples because there's an unlimited number. I could pick 18 apples, or I could pick 6 of each, or I could pick, 4 apples, 11 oranges, and 3 bananas. So whatever it is, that has to be adding up to 18. Right? It's kind of, another way of thinking about it is it's just the number of solutions to this equation where every variable has to be a whole number and not negative. Okay, so that's kind of an interesting, you can turn it into a more mathematical problem thinking of it that way. But what I'm going to do to answer this question is I'm going to develop a little secret communication system for discussing what these configurations would look like. So let me just, for the solution here, I'm going to do what I'll call secret communication. So your family member sends you off to the store, but instead of telling you out loud that I want 9 apples, 4 oranges, and 5 bananas, your family member, instead of specifically spelling that out in words, hands you a slip of paper that has this on it. All right, so there you have it. You've got apples, oranges, and bananas. And what you're supposed to know if you're playing this secret communication system is that this is representing the apples. Then we have a divider, and then this is representing the oranges. And then we have another divider, and then this is representing the bananas, right? So this one would be associated with 9 apples, 4 oranges, and 5 bananas, if I did that correctly. Kind of makes sense? So that would be one acceptable way to come up with 18 pieces of fruit from these choices. By the way, we're only using these fruits. You don't have any other fruits around. It's just these three. So, I'm pretty sure you already kind of get the idea. If I did this. Sorry, it's gonna take a minute. Should have made the numbers smaller. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Can somebody tell me if my family member has handed me this slip of paper? Then what does my family member want me to bring home from the store?
All bananas.
All bananas, 18, nothing in the apples bin, nothing in the oranges bin, there's 18 bananas here. This would be 18 bananas, which is also acceptable, right? That's also acceptable. What I'm trying to show you is that there is a correspondence between a way of doing this, a way of bringing home the fruit, and strings of what are drawn on the board as bars and stars. You have bars separating, making bins, and you're putting the stars in the bins to represent how many of those objects that you have actually picked. So each allowed selection corresponds to a sequence of 18 stars. There's a total of 18 stars there. And 2 bars. And I guess my question then is how many of those are there? So instead of answering the original problem in using the real world terminology, can I answer this question? How many sequences of 18 stars and 2 bars could you actually make?
20 alphabets.
The total number of slots, if you want to think of them as slots, would be how many? 20, right? There's 18 stars and then there's 2 bars. So that would be 20 slots. And I'm putting bars in how many of them? 2. And does it matter which order I put the bars into? I can put this bar here and this bar here, or I can put this bar here and this bar here. It doesn't matter. The bars look the same. I'm just choosing. I'm choosing 2 slots out of 20 to put those bars. And then by default, the other 18 slots must be stars. And that finishes my task, right? The answer is 18 plus 2, choose 2. In other words, it would be 20 slots in total, and I'm choosing 2 of those. And that's the answer. That would be the answer to this. Let's write down the general theorem here and make sure everybody's comfortable with this. At least this time we're talking about combinations and we actually get a combination looking answer. Okay, but you have to be a little bit careful. The 2 is kind of weird. You're like, there's 3 types of fruit and I want 18 of them. Where does 2 come from? Well, what it is really is that you need 1 less bar than the number of different types of objects that you have, right? You have 3 types of fruits. So I need 2 bars in order to make those bins, right? So let's state this one out. This could be a theorem. Just about out of time, but this will be a good way to kind of finish this up a little bit. Theorem 2.5.1, and what this is going to say is let S be a multiset. We're allowing repeats, right? With K types of objects. In a moment, I'll go back to this example and figure out what K is and all the notation, just so we have it spelled out. K types of objects, each of infinite supply. An interesting twist on this problem would be something like, oh, the grocery store only has 16 apples left when you get in there. Right? Well, what you're gonna do is subtract violations. Okay, you're gonna say, you're gonna take this total, you say, I gotta take away any configurations where I went home with 17 or 18 apples, because I don't have that many. So we'll do those kinds of little extensions in a minute, but, or maybe Thursday, but, just at face value, assume that that's not a problem. You have as many of anything as you might want here. And, okay, infinite supply, and then where am I at here? Then the number of R combinations of S is, well, the R is like the number of fruits you want, so that would have been 18, right? And then you have to add to that how many spaces you need for bars, and you need one less bar than the number of different types that you have. So it's going to be R plus K minus 1, and I'm going to choose R here. Or I could just as well choose the bars, which would be choosing K minus 1. And if you don't like that, I'm gonna cheat. The book doesn't really do this, but this is the way you think about it, is that you take stars plus bars and you choose, either the stars or the bars. It doesn't matter. So, in this example above, R would have been 18. And the K, which is the number of types of objects, would have been 3. And so if you plug, I guess you can plug that into the middle one, you're gonna get 18 plus 3 minus 1, which is 20, choosing 2, which is what we said. Yeah. So that's kind of how you can come up with that. On Thursday, I've got to give you, I told you about my soap opera story, right? I didn't tell you about me watching soap operas.
These are the letters.
The last one should be bars in the bar, because we have 2 bars higher.
It's either.
Oh, it's either.
It's either one. This is stars. Yeah, you could put, guys, you could put stars plus bars, choose bars. That's also the same number. That's the same number. Yeah. No, when I was in high school, I watched soap operas. I would go to school all day and then I would come home. And before I started my homework, I needed to take a break and just relax. You don't have to think too hard. You just you almost fall asleep during the soap opera. Anyway, I noticed how the soap opera will always end with some kind of dramatic climax thing going on. And I figured out, oh, this is how they're going to get you to tune in again for the next episode and keep hooking you back in to want to come back. And I realized, that's how my lectures should end. I get you to come back for another class. So on Thursday, we are going to tweak these questions and we're going to say, what if you have to take at least 5 apples and at most 4 bananas? How do those constraints shrink your answer? So you're probably thinking subtracting violations and all of that kind of thing. Yeah, we're going to do all of that. So some of that stuff, some of those earlier tricks, we're going to apply them to these kind of problems on Thursday. So I hope you'll come back for that. I'm headed down to my office. If anybody wants to chat, keep working on the homework. Let me know what I can help with, and I'll see you again soon. Bye for now.